Hello, I'm Floppy. I'm an executable module. And these are my functions.
Hi, I'm Stepper, the runtime system. I also have some functions.
Can I use your function to greet YouTube fans?
Sure. I also want to rule the world. Could you share it?
Nope, it's mine. And I can't.
Let's help them. It's time to implement the complete dynamic loader. Let's begin by implementing the example from the introduction. This example utilizes an already existing dynamic loader implementation. If you missed that, please refer to the attached videos. So, I created a module represented by a floppy. For now, it contains imported functions, do stupid things and greet YouTube fans. And one really simple local function that rules the world. Floppy is an executable module, so he includes the main function. He takes a number of loop executions as an argument. During his main loop, Floppy does stupid things, greets YouTube fans, and most importantly, believes that he rules the world. The runtime system, represented by Stepper, implements function to do stupid things and to greet YouTube fans. Both actions just print. The greeting function seems weird, but still, it's just a print. Floppy uses the sleep function, which is also defined by Stepper. To calculate timestamps, I use a simple method that utilizes sysdig. The sysdig requires configuration, and its reload value should be linked to the core clock. However, I haven't analyzed the clock usage of my simulated hardware, so I have guessed a value that works without any significant issues. I don't need real-time measurement, as it is only used for creating delays. Let's jump to the main program for the test host. As usual, the board initialization process takes place, but this time is followed by the sysdig configuration. The environment provides functions that Floppy uses from the test runtime system. Then, the module is loaded and executed with 5 loops. Let's observe it in action. To ensure understanding of my next steps, I'll explain a crucial aspect of the application binary interface, ABI, related to argument passing in ARM non-EABI. Why we need to delve into this topic? Understanding how the R9 register is filled for position-independent code in a module is essential. Let's consider an example, with a module on the left side and a runtime system hosting the YasLD implementation on the right side. The global offset table is allocated by the runtime system and stored within the module's data. Just before execution, the runtime system looks up the global offset table address for the given module and copies it to the R9 register. When an executable module runs, it can access the global offset table as needed. However, complications arise when multiple modules are involved. For example, if a shared library is used by an executable module, there will be 2 instances of the global offset table, one for the executable and one for the library. The R9 register points to the global offset table of the executable. When the executable calls a function like print, it can access the correct global offset table entry, and everything works as expected. However, when the library is called, an external symbol will also attempt to access the executable's global offset table, because the R9 register has not been updated to point to the library's global offset table. If a function, such as print, in the library module shares the same index as another function in the executable's global offset table, an unplanned and unscheduled crash may occur. Therefore, it's essential to ensure that the R9 register points to the correct global offset table when calling functions from different modules. A straightforward solution would be to wrap each public function inside the module, invoking the PIC register resolver function before the actual call. By doing so, the library module ensures that R9 register is populated before accessing the global offset table. Consequently, access to the print symbol is resolved by the library's global offset table. When wrapping symbols, it is essential to forward all arguments and stack pointer to the original function unmodified. To better understand how the wrapper must be implemented, let's go back to how arguments are passed in the non-IAB specification. There are two cases: fewer than 5 arguments and more than 4. In the first case, arguments are passed to registers R0 to R3 and the stack is not used. The link register retains the caller's return address. When returning from the function, the return value is propagated via registers R0 and R1. In my case, it's only register R0 as long as the integer fits inside. Consider an example function call. Values are passed via registers R0 to R3. The sum is calculated in R0, which is also used to return the output value. In cases with more arguments, additional arguments are passed through the stack. And that's the reason why my wrappers cannot modify the stack layout or registers. There is one more issue. The module cannot access data before the position-independent code register is set up. Additionally, it cannot pass execution normally by function call or callback to the runtime system without the correct peak register. As a solution, I opted to use an ARM interrupt, specifically a supervisor call. This approach provides one possible way to pass control from that place to the runtime system. I utilize the program counter to identify which module requests a global offset table resolver. However, shared libraries require more than just the program counter. Since multiple modules can link to the same shared library, the text section is shared as well. To address this, I leverage the link register to determine the caller. This approach works because cyclic dependencies are disallowed for shared libraries. Additionally, I use this constraint to store necessary data within the wrapper, avoiding heap memory usage. Since I cannot modify the stack, I store this data as a single object within the module's data. Consequently, I pass the caller's R9 temporary registers and the caller's link register, as I need to restore them upon exit. I've employed assembly to generate wrapper code, which proves more efficient and less memory intensive than creating trampolines in C or C++. Additionally, crafting trampoline definitions necessitates a language syntax parser to replicate actual declarations. I utilized GenJ2 as a template language. Initially, I added an architecture specification, and then I employed a GenJ2 loop to generate multiple wrappers. These wrappers are global symbols with temporary names suffixed by _YasLD wrapper. In the final building step, they will be transformed to their original symbol names using object copy. The first step in generating the wrapper code is to trigger a supervisor call. I push the necessary argument registers to the stack, and then I set R0 to the program counter value and R1 to the caller's R9. After that, I push the program counter, R9, temporary register R4, and link register onto the stack. I use the stack to pass arguments for supervisor calls. The supervisor call receives the function ID as the first argument, and the second argument is a pointer to the memory that stores the arguments, which in my case is the stack. My implementation of the supervisor call returns the global offset table address as an element in the input arguments array. Finally, I set supervisor call ID and start of arguments array, and executed supervisor call. Then I receive global offset table address and discard rest arguments from the stack. Nextly, I fill R9 register to point module's global offset table. Next, I locate the entry of the original symbol within the global offset table. The symbol with the original symbol suffix serves as a pointer to the value that holds the offset for that entry. To instruct the linker to populate that symbol with this information, I use a parenthesis syntax with the GOT inside. The ADR instruction returns a pointer, so I need to dereference it. Subsequently, I retrieve the symbol address from the global offset table. Although I cannot use the R9 register as the global offset table for the LDR instruction, due to limitations of high registers, R0 still contains the same value, so I can use it instead. Just before branching to the original symbol, I am restoring original stack layout. Before returning to the caller, I must restore the original register values. To prepare for another supervisor call, I can utilize registers R2 and R3, as they are caller saved and no longer needed. This approach is more efficient than using the stack. Additionally, I need to store registers R0 and R1, since I require them for the supervisor call, and they are transmitting the return value from the original function to the caller. Next, I allocate stack space for the arguments and execute the supervisor call. From the runtime system, I obtain the caller's link register, the value of R9, and the temporary register R4. Let's restore these registers along with R0 and R1, and then jump back to the caller. The task is complete. My wrappers trigger supervisor calls that must be handled by the runtime system. I've implemented a simple approach that just selects the correct YasLD handlers function. Let's examine the implementation of the actual call handlers, defined in YasLD. Firstly, I create aliases for the arguments in an array. Then, I have to find out which module triggered the supervisor call. Unfortunately, I can't directly pass the information from the module itself, since it can't access any data before position-independent code register fill-in. Although there should be a panning mechanism, it hasn't been implemented yet. Afterward, I store the caller's data under the module and mark it as active. Finally, it's time to return the global offset table address. The exit handler utilizes an activity flag to determine which module triggered the call. Again, there is no panic yet. Then there is module deactivation and the caller's data is returned in the args array. Let's check the diagram to understand the necessary steps for placing wrappers in the final module file. Firstly, the build system must compile all source files. Then, using a cmake preling action as a custom command, I call a generator script for each object file. This script generates a static library containing the wrappers. After generating the static library, I link the wrappers to the module. Finally, as the last step, I swap the original symbol names with the corresponding wrappers. Let's step through the cmake code that calls the wrapper generator. I've organized it as a function that takes the target as an argument. Within this function, I add a custom command with a preling action that executes the generator script. Additionally, I've included dependencies on both the script and the template file, to ensure that the wrapper will be rebuilt whenever either of those files is modified. The same function also adds a post-build action for swapping names. Regarding linking to the static library, I use the full archive flag to prevent the linker's garbage collector from inadvertently wiping out my precious wrappers. Now let's delve to the generator script. As always, I capture the necessary command line arguments. Since the script builds a static library, I also need to pass the compiler along with its flags. Currently, I allow multiple input files to be specified at once, separated by commas or semicolons. However, I should consider changing this to use an args for a more flexible approach. Let's go to the heart of the program. Firstly, I load the template file for the generator. Then, I parse each input file using the elf parser created in the previous episodes. During this process, I skip symbols that are already wrapped. I restore their original name and position them for wrapper generation. Next, I seek out symbols that represent public functions. When found, I add them to the requested list. Subsequently, I call the wrapper generation process for each file and export all wrappers to a single file. Finally, the resulting file is compiled and placed in the static library. However, I should consider using object files instead. In the names fixing script, I locate the wrapper symbols and then change the original symbol names by appending the suffix YasLD original. These original symbols must remain hidden from the word, since they cannot be used directly. Finally, I changed the wrapper names to match original names. I added support for dynamic section parsing inside the ELF parser. I plan to use shared libraries. However, it turned out this feature is not available on ARMv6-M processors, as the GCC toolchain doesn't support procedure linkage table on TAMP1 architecture. The procedure linkage table, PLT, is used to optimize library loading. It enables lazy loading, which is beneficial when dealing with libraries that contain hundreds or thousands of functions. However, in practice, only a few of these functions may be used by the user application. Interestingly, even if fno_plt flag is added, the TAMP1 shared library generation still fails. This issue prevents the proper functioning of TAMP1 shared libraries. To create a library without PLT, I employed a workaround. I compiled the libraries as executables with exported symbols. This approach allowed me to use the global offset table without relying on PLT, and it's functioning for now. In the future, I intend to explore whether I can enhance my wrappers to enable calls through a form of PLT. I've incorporated support for dynamic sections in an executable linker script. This addition is harmless when the PLT is not used. Furthermore, there is hope that someday PLT support for TAMP1 architecture may be added. Subsequently, I duplicated the linker script for the shared library. The sole distinction lies in the fact that the shared library linker script does not specify an entry point. The dynamic loader now needs to manage multiple modules. It's time to extract the module's data into a separate module base class. To store these modules within the loader, I utilize an observer list from embedded utility libraries. This observer list keeps tracks of observed nodes without allocating memory for its elements. Instead, it watches objects allocated elsewhere. The implementation uses a double linked list. Thanks to these characteristics, the observer list dynamically adjusts its size without relying on heap memory. Additionally, when a tracked object ceases to exist, it is automatically unregistered from the list. I created separate lists for executables and libraries. Next, I introduced an interface for libraries and updated existing interfaces to propagate the concept of modules. Additionally, I implemented a function to verify whether a given program counter belongs to a specific module. As part of these changes, I removed the module's data from the loader. This fragment of code checks whether the program counter belongs to the text, data, or BSS section of a module. Additionally, the findModules function iterates over executables and libraries to locate modules associated with a given program counter. Then, I created a base class for both executables and libraries, as they share similarities. To tackle memory leaks, I introduced allocators for use with STL containers, replacing the previous method of allocating memory without proper deallocation. Subsequently, I transferred the module data from the loader to the module itself. The foreign call context now holds essential data when the wrapper for a public function is invoked. This context is utilized by the supervisor call handler, which I previously discussed. Naturally, I also migrated loader methods related to modules. Finally, I added a method for searching symbols within the module and for saving the foreign call context. I inherited a module within an executable class. Although there haven't been significant changes to the executable, it has received new inherited data. Additionally, I've begun creating a library class. This library class is designed to handle symbols importing, and I've introduced a template helper class to simplify the process of importing symbols. One important consideration is that the runtime system might lack access to headers, so we must specify function declarations independently. This approach bears similarity to the behavior of Linux dlsym function. Allow me to provide an example of how I'm utilizing this. Assuming we have the declaration of cfun, the symbols obtained from the module would resemble the one listed below. Subsequently, the invocation process remains identical to that of a regular function. Since mkimage now requires specifying a module type after the latest changes, I've added a parameter for the convert_elf to YasIf function.
I have an idea. Cat Guardian, could you help me?
Hi, what is it?
Could you spawn cats for me?
Are you talking about that function?
Yes.
Then sure.
Yippee!
Moving on to the implementation of example 2, our new library features cat spawning functionality. It accepts an ID for cat selection and a prefix for login. The implementation is straightforward. We simply select and print relevant picture. In the second example, only the runtime utilizes a shared library. It dynamically loads and calls functions from the library. We can verify that multiple calls work seamlessly. Meanwhile, I needed a more powerful board for my tests, with greater memory capacity, so I restructured them to support various configurations. The tests are now categorized by architecture, microcontroller family, and specific board.
Could you please add a full dynamic linker to convince Floppy?
Absolutely, let's get started!
Yippee!
I made some changes to the format file by introducing a name for dependency resolution. After that, I converted the elf to YasIf function to a macro, which allowed me to use CMake variadic arguments. I had to do that to add readable dependency management for shared libraries. I can't use CMake dependency management due to issue with unsupported PLT. Then I made some changes in mkimage. Firstly, I captured dependency list. I extended the skipped relocation list. Furthermore, I introduced relocations toward exported symbols, as they appear to be necessary. Finally, I ensured that dependent libraries were propagated to the image file, allowing the runtime system to resolve them. As you've noticed, I've added custom allocators. Let's take a closer look at them. Firstly, I implemented these allocators using EOL function and organized them within a singleton object. Next, I created an allocator implementation that adheres to the interface required by STL containers. Additionally, for smart pointers, I designed a custom deleter. To address the loader's requirement for obtaining dependent library files, I introduced a callback mechanism from the runtime system. Subsequently, I implemented several methods to facilitate module searches based on specific requirements. Expanding further, I extended the load module method to load the entire dependent tree. Of course, I verified that runtime system returned correct YasIf file. Notably, I allowed for scenarios where executables serve as children of other executables, even though conventionally an executable should not be a child of another executable. Symbol searching was extended to look for symbols inside child modules. Then I implemented methods of searching modules. Next, I extended the module to maintain information about child modules and introduced methods for searching these child modules. Additionally, I expanded symbol searching to encompass children modules. Finally, I finished the implementation of module searching methods and added support for name in parser.
Floppy, look who joined us! Oh, can I also spawn cats? I can share my word ruling function in exchange.
Of course.
Now let's delve into the final example implementation. While Floppy dynamically links some libraries, it still allows linking static libraries to the modules. Additionally, I've ensured that the include directories from the cat spawner and rule word shared libraries are propagated to Floppy. This enables Floppy to use them along with the shared libc. Subsequently, due to the word ruling functionality being relocated to an external library, I removed its implementation from Floppy. Instead, I've used the possibility of spawning cats. For those intrigued by my microcontroller firmware creation process, I've included a layout parameter that specifies the addresses of the relevant modules. Now, with the runtime system no longer requiring the propagation of libc symbols, I've removed them from the environment. The system needs to propagate a callback for resolving files. This callback method examines the name and provides the hard-coded address of the requested module. And now Stepper can also wield word ruling power, not just floppy. And they lived happily until I pressed Ctrl+C.